Okay, so let's do some work with fractional, negative and fractional exponents. Let me give you some notes to remind you of why a negative exponent works out the way it does. How come a negative exponent means reciprocal? So one way to look at it is here, x to the third over x to the fifth is clearly x to the negative 2 by subtracting the exponents. But if I write out x to the third, I get xxx, and x to the fifth, I get xxxxx. And then if I cancel out, kill, whatever you want to say, with these x's on top, that leaves just the xx on the bottom. So that's 1 over x squared. So therefore, x to the negative 2 is going to mean or equal 1 over x squared, which is why 5 to the negative 2 is 1 over 5 squared, 1/25. It's reciprocal. So remember what we used to teach in school? If I ever had a situation where I was teaching negative reciprocals, I would yell like a Marine Corps drill sergeant, because some things are just best learned that way. A negative exponent! And the class would yell, reciprocal, sir! So the reciprocal of 3/7 is 7/3, and then once I take the reciprocal, it's no longer a negative exponent, it's a positive. So 7/3 squared is 49 over 9. With that in mind, let's try these three. Go ahead. Okay, so a negative exponent, this is 1 over, or reciprocal, 4 to the positive 3. Now, if you wanted to give a value for that, it would be 1 over 64. But a lot of times the instructions just say to express it as a positive exponent. So that would be 1 over 4 to the third. 10 to the negative 2, a negative exponent, 1 over 10 to the positive 2, which if you went all the way out and wanted a value, would be 1 over 100. And then 2/3 to the negative 2, that would be, the negative exponent means flip it and square it. So that would be 3 squared over 2 squared, because I flipped it, right? It was 3/2. Oh, it was 2/3. I'm sorry, it was 2/3. Then I flipped it to 3/2, got rid of the negative in the exponent, and 3 squared is 9, 2 squared is 4. Okay. First 4, we'll do them each piece at a time. First one, express those as a fraction. Go ahead. Remember, we're working on stop and start time here, so I don't have to wait forever. First one, that'd be 1 over 23. Second one, 1 over m to the 99th. Remember, a negative exponent never means put a negative in the answer. It has nothing to do with changing the signs or negating answers. It has everything to do with reciprocals and flipping. So 23, the reciprocal is 1/23. M, the reciprocal is 1 over m. Next one, p to the negative 5, the reciprocal is 1 over p to the 5. And then 12 is 3t to the negative 1. And the key point to get here is that that exponent only refers to the t. It does not refer to the 3. So that's 3 over t. Now try the other direction, 15 to 24. Go ahead. Okay, so the first one would be 4 to the negative 4, then m to the negative 4, then 7 to the negative 2. Hopefully you recognize that the square root of 49 is 7. And then 24 is 13 to the negative 2. A little trickier to know that the square root of 169 is 13, but after you notice how 21 was done, you could use your calculator to help you out. What about fractional exponents? Remember, kindergarten play, the roots of the tree are down. The power is in the leaves. So, when I get an expression like this, 8 to the 2/3, it's the cube root of 8, because the roots of the tree are down, cube root of 8, 3 is on the outside, and then it's 8 squared on the inside. And you could do this either, if you wanted to square it first, you could do 8 squared 64, and then the cube root of 64 is 4. I don't like doing it that way though. I like doing roots when numbers are smaller. So the cube root of 8 is 2, and then 2 squared is 4. All right, and that just summarizes what we did. All right, so let's express in radical form. They're not asking you to evaluate it, they're just asking you to express it as a radical. Numbers 2 and 4. Go ahead. Okay, so first one, the roots of the tree are down. So it's the square root of 25 cubed. And the other day I put the little 2 out there as a point of emphasis. Now I'm not doing that because we all know if there's no number written outside of a square root, it means 2. And the next one, negative 3/4 power. So the negative means I have to flip it. So that makes me make this 4 over x instead of x over 4. And it's the 4th root because that's what's down. And then that whole 4th root is cubed. Okay, now we're going to put it in radical form and have you put it in exponential form. Go ahead, number 6 and 8. Cold in my room. Okay, so the root is 3, the power is 7, so that's 3 to the 7/3. The root is 3, the exponent is 6, so that's y to the 6/3, which does equal y to the 2, right? Okay? All right, so now let's explore exponential equations. And we talked a little bit about these the other day. There's 2 types. There's the variable in the base, which is what we did the other day, and then there's the variable in the exponent. So let's do a quick review of the variable in the base. I'll work through the first one with you, and then you will get a chance to do a second one. So this is kind of like a radical equation, which makes sense because in a form, an exponent, a fractional exponent, is like a radical. It's more than that, but there's enough similarities. So the first thing we're going to do is isolate. Subtract 5 from both sides. That gives me x to the 2/3 is 25. And the skill we learned the other day is when we want to have this variable in the base, we want to raise to the reciprocal of the power on that variable. So this says 2/3, so I want to raise both sides to the 3/2. And that's what I did here. 2/3 I raised to the 3/2, 25 I raised to the 3/2. Now, the squares will cancel each other out, the 3's will cancel each other out, they're gone, leaving just an x on the left. And you just need to compute, well, what is 25 to the 3/2? Roots of the tree are down. Square root of 25 is 5, and then cubed is 125. And you could, if you wanted to, just take your calculator and type in 25, and then that caret symbol, which is found under the clear button on the right side of your graphing calculator, just do 25, up arrow or caret symbol, 3 over 2. Just do 3 divided by 2, and it'll tell you 125. Okay, you try the next one now. Go ahead. Okay, so I'm going to add 1 to both sides. That gives me 2x to the 3/2 is equal to 16. I'll divide by 2. And that gives me x to the 3/2 is 8. And then I raise each of those to the 2/3 power. On the left-hand side, 2/3, 3/2, that cancels each other all out. That leaves me with an x. And on the right-hand side, the cube root of 8 is 2, squared is 4. Okay. So those are 2 good solid examples to get us started along the right way, but I don't think it's enough to know it inside out, backwards, and forwards. Let's try these 2. Go ahead. Okay, so we're continuing to work on these problems where the variable is in the base itself. Later we'll get to when the variable is in the exponent, but for now, variable in the base. Subtracting 5, x to the 2/3 is 81. Raise both of them. Since the exponent here is 2/3, you raise them both to 3/2. Okay, 2/3, 3/2, they're going to cancel each other out, and I get x is the square root of 81 is 9, and 9 to the 3rd power is 729. Okay, again, you could just put that right into your calculator. 81, up arrow or caret, 3 divided by 2, there's your answer. Next one, add 7 to both sides. Divide by 2 to both sides. And I get x to the 3/2 is 27. So now I go to the 2/3 because it's the reciprocal of 3/2. Die, and I get x is equal to, the cube root of 27 is 3, squared is 9. And again, you can just put that into your calculator. So I suspect that by now you're getting more comfortable with these fractional exponent equation type of things. Let's now go to the last equations with exponents kind of questions we're going to deal with. Variable in the exponent, the common base. Okay, so the big difference here, you'll notice it says 5 to the x. Now the variable's in the exponent, or 4 to the x plus 1. Again, the variable's in the exponent. And there's a completely different technique for doing this kind of question. And it's something that it helps a lot to be able to recognize. If you don't recognize the common base, these are very difficult. But if you're able to recognize the common base, they're not hard at all. So, first one, isolate it, just like before, subtract the 7, and I get 5 to the x equals 25. And here's what you're going to do. You're going to ask yourself, is there a way to express whatever's on the left side, the base, and whatever is on the right-hand side in terms of the same base? And in this case, yes, you can. That base is 5. 5 to the x is going to equal 5 squared. Now, once the bases are equal, in order for the both sides to be equal, then the exponents have to be equal. So get the bases equal, then once you have that, you can make the exponents equal. And that means that x has got to equal 2. Let's see you try the next one. Go ahead. Okay. Now, add 3 to both sides, and that'll give me that 4 to the x plus 1 is equal to 32. And you say to yourself, well, in the last problem, 25 was a power of 5. 32 is not a power of 4. But they're both a power of 2. 2 squared is equal to 4, and 2 to the 5th is equal to 32. So I get 2 squared to the x plus 1 is equal to 2 to the 5th. Well, when you raise a power to a power, you multiply, so that'll give me 2 to the x plus 2, 2 to the 2x plus 2, sorry, is equal to 5. And now I have common bases. And once I have those common bases, then the exponents have to be equal. So 2x plus 2 has got to equal 5. And then you just solve it. Subtracting the 2, dividing by 2, and I get x is equal to 3 halves or 1.5. All right. So I know that this is a little challenging here, particularly the one we did on the right-hand side, but you're isolating like before, and then you're finding a common base. The left-hand equation was easier because it was pretty obvious what that base was. It was one of the two terms, namely 5. But on the right-hand side, it was more challenging because both 4 and 32 were powers of a smaller base, and you have to be able to handle that. Okay, so I have 6 questions here, and in each case underneath the rectangles are the solutions. So let's have you try the first one. Very nice to you on this first one. They give you the common base. In fact, for the first 4, they give you the common base. So as soon as they give you the common base, all you need to do is set the exponents equal to each other. Okay, so again, we're doing stop and start here. 3 minus 2x is going to equal negative x, and that works out to x is 3, right? You're going to add 2x to both sides, and you get x is equal to 3. Try the next one. So on the next one, the exponents are equal, and I get 2a equals negative a, so a is 0. That delay really messed me up here. Let's look at the next one to show it to you. On number 3, the exponents are equal to each other, so I should say the bases are equal to each other. So once they are, the exponents have to be. So 2p will equal negative 2p minus 1. Add 2p to both sides. 4p is negative 1. Dividing by 4, p is negative 1/4. Okay, try number 4. Again, bases are the same. So negative 2x is going to equal 2 minus 3x. Once you have the bases equal, the exponents have to be equal. So we're going to add 3x to both sides, and I get x is 2. All right, so number 5 is the first one that's any kind of challenging on this. These are not particularly hard because in both numbers 5 and 6, the common base is part of the problem. You don't have to go simpler. We'll get to those next week. But now, try number 5. Go ahead. Okay, so 2 is the common base. So 8 becomes 2 to the third power. Okay, so the teacher that did this, they left a little bit of work out. So let me explain here. 8 is 2 to the third, okay? And then when I raise 2 to the third to the x minus 1 power, I distribute that 3 to the x minus 1, and I get 3x minus 3. So now I have my common base, so the exponents must be equal. So I get 3x minus 3 is x plus 2. Subtract the x from both sides here. That gives me 2 x's. Add 3 here. I get 5. Dividing by 2, and I get x is equal to 5 halves, or 2 and a half. Okay, try number 6. Another little bit on number 6 there. Okay. Now, raising 12 to both powers here because they're both a power of 12. 144 is 12 squared. So they take the squared, and rather than write out the step, they just distribute it right away to the exponent. So 2x plus 1 times the 2 for the squared there is 4x plus 2 is equal to 12 times 5x minus 1. Since the bases are the same, the exponents have to be the same. 4x plus 2 is 5x minus 1. Subtracting 4 from both sides, I get x on the right. Adding 1 to both sides, I get 3 on the left. So that is 6 examples of finding the common base so that when the variable is in the exponent place, I can figure it out. Okay. Happy recap. If the variable's in the base, what's the strategy that we use to solve? Well, if the variable is going to be in the base, okay, as opposed to what if the variable is in the exponent. If the variable is going to be in the exponent versus variable in the base. If the variable's in the base, that's when we want to take the reciprocal of whatever the power is. And if it's in the exponent, then we want to get a common base. And number 3, with 2 lessons, 1 pretest and 1 test in a week of course review and a final exam remaining. If you got something I can do to help you, feel free to send an email. What can you do? For a lot of you, it's just keep doing what you're doing. And if it's not, if you're struggling, then, think of what you can do. The one thing you cannot do is do not ask me for extra credit. It's not going to happen. The only thing I ever said to you that you could do to boost that grade a little bit is get all your homeworks in. So if you don't have all your homeworks in, get them in, and you'll get half credit for everything that's late returned back to you. All right? Have a great one, folks. Hasta la bye-bye.